Yeah, unfortunately, I'm not allowed to talk about what the intrinsic does. You know, it's just the first round of their the spin-off just started. So, but I'm gonna talk about my PhD work.
Of course, please go ahead.
Yeah. Okay. Hi, everyone. As Karin said, I'm Gaia. I'm from Michael Bitz's group. I'm in my final writing phase of my PhD. And yeah, thanks very much for inviting me. It's a pleasure to be here. Yeah, so this talk is about how you can utilize semantic representations to make your plans, robot action plans, scalable and transferable. And in general, when you are developing the high level of your robotic software system, basically the executive layer or the planning layer, people also call it, you need to make a choice between imperative representations such as state machines, behavior trees, or scripts or programs, and declarative representations such as plans in classical AI or task and motion planning sense. And declarative representations have a lot of advantages with respect to the imperative representations. But on the other hand, they also have disadvantage that they are more complex and they need more engineering effort. And in this talk, I would like to present my approach of how you can take imperative representations and add semantic descriptions to them to get some of the advantages of the declarative representations without having to introduce too much complexity. Yes. So I will start by presenting the overall problem that the approach is aiming to solve, and then I will present the two core concepts that the approach is based on, and these are the symbolic entity descriptions and task trees. And then I will talk about the advantages that they bring with them and the applications of these two core concepts. And I will conclude with lessons learned, and then we'll have hopefully some time for Q&A. Yes, so what is the problem that I'm aiming to solve? The overall goal is to develop plans, robot action plans, that are reusable, that scale when you increase the domain, the application domain. So basically, when you add new objects to your application, when you change the environment, when you change even some parts of your robot hardware or completely the robot platform. And basically, for example, we can have one plan, which is to transport any object of any type in the environment that the robot physically, obviously, is able to manipulate from any location in the environment A to any other location B. And here we have videos of 3 different robots in 3 different environments. Here we have a household application in a kitchen. Here we have a assembly application. And here we have a retail application in a supermarket. And all these robots are executing mobile pick and place plans with the same exact plan. So the plan program is the same. We have lots of different variations and kind of execution domains. And the question is how we can ensure such scalability in the plan. Okay. So as I mentioned at the beginning, we use imperative representation. So in my case, we have our plans are just programs. So we have we support 2 programming languages, Lisp and Python. So these are either Lisp programs or Python programs. We have a perform operator to which you can pass in motion description with some constraints and so on, and then it will execute this motion on the robot. And then we have all sorts of different DSL operators, domain-specific language operators, which are basically wrappers around the multithreading library of the underlying programming language, which are like syntactic sugar for us to write concurrent reactive plans. But we are not going to go into detail here. I just wanted to explain that the plans are kind of engineered programs. The failure handling is also more or less like try-catch blocks, and we have additional operators such as this retry to make the plans more compact. Okay, and then obviously, as you can have hierarchical nested function calls, you can also have plan calls. For example, here the pickup plan is consists of calls to perform low-level motions, which is this level of the hierarchy in a sequence or in parallel. And then the higher level plans are comprised of calls to lower level plans. And then, for example, the transport plan will call its lower level subplans. The problem with this approach is that if you think back to the videos that I showed with the different environments and the different robots, if you approach it in this way, your plans will get really huge and complex and difficult to read. So in order to make them more scalable and more independent of the execution domain, we introduced this concept of symbolic entity descriptions. Here we have, for example, a symbolic description of a primitive motion, which you already saw such like motion descriptions in the previous slides. We have primitive motions and primitive percepts, like perception actions. That's why I call them primitives. So the API is the same for both perception and motion planning and execution. But here, for example, we have a primitive of type pouring, where we want to pour from this source container into this destination container, and we will have some motion constraints on the trajectory, such as don't tilt too fast, and that the destination container should be half full by the end of the motion execution, and so on. And these are all described in this kind of semantic symbolic key value pairs. And then we have semantic descriptions of objects, which are again key value pairs with basically a description of the object. And we can pass this to the perception system to find an object that satisfies these constraints in the current camera view, or we can pass it to the inner world state, the belief state of the robot, to look up an object from the set of objects that the robot knows about that satisfy this description. And then we can also describe locations in symbolic semantic ways. Here is, for example, a location for the PR2's base to stand on the floor such that the PR2 can reach the given object. And here you see this is like Gaussian distribution part from which we can sample poses that will then all satisfy these constraints. And then you use these data structures in the plan, and at runtime, they get grounded into the specific execution context. For example, a location will be grounded to a specific 3D pose in the current environment of the current robot, or the object will be grounded into an instance in the inner world state, and primitive description will be grounded into a call to the specific controller with given parameters and so on. And basically, by using these, you achieve some a sort of an abstraction layer over your execution domain in your plan. And then we also introduced action descriptions, symbolic action descriptions. As I mentioned before, the plans for us are implemented as functions, and these go on top of the functions. So for example, we have a pick up plan function, and then on top of it, we have an action description of type picking up. And then the parameters of that plan we specify here. The optional parameters we leave out. And then during execution, before we can perform this action of picking up a cup, all the missing parameters need to be and will be inferred. For example, with which, like, do I pick the object up from the top, from a side, with one hand or two hands, and so on, with how much effort. And then all these parameters that are inferred will be passed to the plan function. An important part of this description is the goal statement. In declarative planning, the goal statement is extremely important, and you cannot omit it, but it is often difficult to declaratively represent the effects, the intended effects of your action, especially if it's a complicated, well, complex manipulation action such as cutting or polishing a surface and so on. But so in our system, these goal statements are optional. But if you can represent the effect declaratively, such as in this case for a picking up action, we just want the object that we are trying to pick up to be in the hand, if the robot's hand, then you specify it. And then before executing the action, when this perform operator is executed, the goal is checked. This predicate object in hand is evaluated with respect to the inner world state of the robot, so the belief state. And if it already holds, then you just skip this. And then, and that is a great performance improvement such that, yeah, you can skip all the actions, the goals of which have already been achieved, obviously. And you can also use this goal statement for evaluating if your action has been achieved after you performed it. So basically, if the goal statement holds or not, and if it doesn't, then obviously something wrong happened and you throw an error. Another advantage of these action descriptions is that you separate the data processing, the inference of the object, of parameters, basically like the arm, the grasp type, the effort, and so on, from the plan. So this step happens first, and then all these parameters are passed to the plan. And as a result, we get the clean separation between the control flow and the knowledge. So the control flow is all the steps of the action. Basically, you know, if I want to transport an object from A to B, I have these steps: search, fetch, deliver. And all the optional parameters of this action are inferred separately in the knowledge processing system or the question answering system. For example, the search action needs to know where to search for the object, what's the likely location of the object. And then, yes, we query it, we query the QA system and get the result back, and then the plan executes this action. And as a result, we get kind of modular code. The plan and the knowledge processing are separated. And the kind of this data processing is very explicit in the plan. So if you subscribe to this communication, you get a very good insight into the decision-making processes of your robot. So you see all the information, all the data that the robot needs, and what it got as like which parameter values it got. In addition, your plan gets really slim. It only contains the steps of the actions and what to do if a failure happens, so the failure handling strategy steps, and it makes manipulating the plan easier if you want to optimize the plan, for example. And I will give an example in a second. And then based on these action descriptions, we can build the so-called task trees. And these are a runtime representation of all executed actions in the plan. So every time you perform an action description, a node is automatically created in a tree. For example, when we perform a transport action, a node is created, and then its child search and fetch actions, and so on. And the hierarchy is also preserved in this data structure. We store not only the type of the action, but also the outcome, if the action succeeded or failed, and all the parameter values that were used. For example, when we were fetching the action, fetching the object, with which hand we fetch the object, and so on. And using this data structure, you can then do cool things like online simulation-based reasoning. So you spawn a little simulator run based on the current state of the world. So this is the real world. This is the inner world state, the belief state, and then you spawn from this n runs of a simulation, and you execute an action, for example, your pick and place, in different variations, and you vary the parameters. For example, you pick the left hand or the right hand, you pick a top grasp or a side grasp, and so on. You vary the poses of the robot's base, and then you execute these actions in simulation, calculate the costs based on the parameter values, and then pick the run that was the best. And the advantage of these task trees here is that you can extract any parameter value from any layer of the hierarchy by crawling this task tree. So if you need, for example, to know where the robot was standing in when he was perceiving the object, you don't need to pass this value back to the parent and propagate it up as you would usually do, but you can just crawl the task tree, find the necessary information, and calculate the cost and pass this information to the real robot execution. Out of time constraints, I'm not going to show the video, but if you are interested in how this works, we can just go back in the Q&A round. The important thing here is that the simulation needs to be quick. In our case, the simulator is discrete, so it's about 50 times faster than real time. So you get these runs, the answer of this reasoning within a few seconds, and then your execution doesn't visibly stop. The next thing that you can do with these task trees is you can, it simplifies drastically collecting training data. So here, for example, we see a location. If you remember these symbolic location descriptions, for example, this is a location to open this vertical drawer for the PR2. And this distribution is generated via heuristics. So it just says, you know, stand with this radius away from the handle, where the radius is the length of your arm, and some padding to cut away collisions. And then you can sample from these locations and execute the same action multiple times in different variations. So here we can see opening the door and picking up an object in different, like in different samples. This is the left hand, the right hand, different robots, and so on. And if you simply log all the how do I? Oh no! I'm using Google Tools. The internship is rubbing off me. Present. Loading. On. No. Oh, there we go. Maybe it's, there we go. Yes, so I just showed you how we collect the data. And the thing is, you only need to log this task tree. Because you collect all your parameters of the actions are contained within this nodes of the task tree, except camera images. But until now, everything that we learned, all the data was kind of accumulated in these nodes of the performed actions. And then we collect the different success and failure rates, obviously, and then the location distribution for the same action based on the heuristic data and the learned, I mean, here it was some kind of a very simple model, turns into this Gaussian. And another very important thing that is advantages in declarative approaches, in declarative planning, is that you can easily optimize your plan. So you can take the execution, find a better way to do it, and execute that on the robot. And if we assume that we just do it in an imperative way, so for example, we have a plan to transport a ball from this back surface counter to this table, and we need to do it twice for 2 balls, then obviously we will just call the pickup function twice, and then the robot will do it like this in a sequence. But if the robot has 2 hands and the objects are small, you can obviously just bring both objects at once. And like this, or you can even use a tray and collect multiple objects first on a tray and then bring the tray. And the most obvious way of how you can kind of introduce this optimization, implement this optimization, is if you use like abstract syntax trees and directly modify the code of your plan. But this is error prone, this is complicated. But if you have a task tree like this, where we can see the robot was transporting a milk box and a cup in a sequence, so fetch milk, fetch cup, deliver cup, you need to only take out this node, plug it in here, and then you will get already your optimized behavior right away. So you will fetch the milk, then you open the milk box, then you will fetch the cup, and then you will deliver both objects at their destination. Of course, you need to ensure that the locations, the destination locations and the source locations of these 2 objects are close to each other. Otherwise, it doesn't pay off. But yes, and this kind of optimization is very easy to make. You just take out the node and put it here. And yeah, and that implements it. And I think I'm already out of time. So I'm going to skip conclusions and the summary and just right away jump into the Q&A session. So if you have questions, please.